of the best paper nominees. So go ahead and make sure that you take a look at the written form, because that's the way that we surface the nomination for best paper. And of course, those are being announced later in the conference. So we'll move to remind some of you who maybe just walked in expecting to hear from Tanya Kaser for modeling exploration strategies to predict student performance within a learning environment and beyond. Not here. Instead, we're moving right to our third presenter, in truth, our second, who is Charles Lang from Teachers College at Columbia. And he is going to be speaking to us about opportunities for personalization and modeling students as Bayesian learners. Take it away, Charles.
Thank you very much, Stephanie. Yes, shockingly, I am not Tanya. The first thing I'd like to say is that this is bananas and quite amazing. That the kind of modeling section of this conference has historically been a dinky little affair with a few people, and this is actually incredible, so congratulations to you guys for turning up. And it looks like it's a real diversity of interests, so I'm kind of blown away. Not to waste an opportunity to shamelessly plug something, this is the Handbook of Learning Analytics. It has theory, application, and modeling sections. So anyone interested in student models, check it out. It'll be up online in a couple of weeks. There's a little flyer with the URL in your conference bags. So I'm going to talk about something that's a little bit left field in modeling. It's kind of the opposite, it's kind of the inverse of what we just heard about. So the idea that we would take a whole lot of data and we would then try to carve out from the variation statements that we could make about individual students. This strategy is totally experimental, totally a little bit out there maybe, but it's going the opposite direction. So if we only had one student and we only had the variation associated with one student, could we make any credible probability statements about that student? So this is pertinent to the idea of personalization, which I'll put up this slide, which is just to demonstrate that we've been at this idea of trying to make individual statements about students for a fairly long time. Here's a quote from 329 BC. The success of education depends on adapting teaching to individual differences amongst learners. So probably not going to solve it today, but yeah, I think it's worth thinking. Also, a few years ago, quite a few years ago now, 2010, the US Federal Department of Education took a stab at trying to contain the definitions of these words. I don't think they were particularly successful. I think people kind of use them interchangeably. They created these definitions that individualization is learning goals. Everyone gets the same learning goals, but students get to go at different paces. Differentiation is the same learning goals, but the methods differ. And whoa.
Oh, we lost someone.
Are you okay?
Okay.
Okay, we're all right.
No, they're dropping like flies
Yeah, apparently.
in the session.
It's that amazing. My voice is that amazing. It makes people fall over. It's like kind of narcoleptically, I imagine. So we've got these ideas of kind of personalization and differentiation, individualization. I think the bottom line from the kind of modeling perspective is that we want to be able to make a probability statement about an individual. And the issue with that is that an individual can only ever do a task one time. They're kind of stuck in time, and we can't reverse time, change the conditions a little bit, and then do it again with them, and then develop a distribution around them that way. So what do we do? We tend to do things like, because we want to come up with this statement, like the probability Beverly will answer the question correctly is X. And so the way we kind of fudge it in our minds is that the probability represents counterfactuals, hypothetical counterfactuals of what would happen to Beverly, and the actual numbers are derived from a population that we can reasonably expect Beverly is like. And that's kind of how we generate our probability statements for individuals. But what I wanted to do is ask the question, if we didn't have any other individuals, could we still make some kind of probabilistic statement about a student. If that was the only student that we had, they were stuck on a desert island with me, worst case scenario for their life, but would I be able to make some kind of probabilistic statement about their learning or the way that what they know? And in that case, the only variation we have is the variation across time, the kind of sequence of answers. So I'm going to explain the model that I came up with to do this, and I'm going to explain it in 3 different ways, and hopefully that will clarify how it works. I'm going to kind of explain it in the kind of as an abstract model, a kind of dinner party version, which gives some kind of intuition. Then I'm going to explain the operational model in terms of what we would count as an example. It's just one example. There might be many ways of doing it. And then the validation model, how we can know that it's actually working the way that we think it should. So the abstract model is an old one. It's this idea that people might be Bayesian. And the first step in that kind of sequence is to say, well, probability isn't just a fraction of a set of things. It's not just some kind of count. It's actually a property of things. And in our case, it would be a property of students. So students have some kind of probability of doing something, which is something they carry around with them. The first person that I can find who kind of put this model onto the educational context is Di Finetti in 1965. And we set up this situation where we've got 3 pieces that we need to fit together. One is the behavior that the student is doing. They're doing some task, maybe they're answering a test, and there's a probability that they will exhibit that knowledge. So that's what we get to see in the world. But also they must hold some kind of prior knowledge, like what did they bring to the table? And that's going to exist in their mind somewhere. And then there is this likelihood of them processing their context and incorporating it into their prior knowledge. For people familiar with Bayesian statistics, next to the things are the probability statements. But I'm going to have a couple of goes at trying to explain this so that lots of people can understand. So this is what our model of our student looks like in terms of Bayes' rule. We've got some kind of behavior, in the Bayesian terms would be called the posterior, and it's proportional to the likelihood and multiplied by the prior, which is our context, which is the data given the knowledge that the student has. And this is the bit that it becomes controversial, which I'll explain in a minute. But yeah, and then that's multiplied out by some kind of prior knowledge that the student has, which is probably the thing that we most care about. That's the thing they're carrying around with them that they're going to use to answer questions, but the context is going to do something to them, which is going to combine with the knowledge to produce whatever behavior. So here's my kind of intuitive understanding of that concept. And right there, this person's trying to figure out, was that some kind of accident or was that person? So was that on purpose or was it an accident? So we can kind of think of this again as we've got some kind of behavior. Was it purposeful? Did it come from knowledge? Or was it some kind of contextual thing that pushed the student towards or away from confirming their knowledge? In the kind of educational context, we can think about a test, that there are kind of things that we might consider a knowledge, like that are purposeful, the knowledge, kind of coordination, planning, coming up with how we're going to answer the question. And then there's a bunch of distractions. There's things out in the world that maybe you interpreted the question incorrectly, maybe you were distracted, maybe you misread the clock, something like that. So the difference here is that for each student, we're framing the question, the modeling question, in terms of we need, for any given behavior, which are the lines on the side, there's a probability associated with it. And we need to position the ratio between knowledge and context. So we need to figure out, okay, we're on this curve. Where on that curve does this particular student lie? And that's what our model is going to try and figure out. If we can position them accurately, then we'll be able to predict their behavior accurately. If we get the wrong mix of knowledge and context, then we won't predict accurately. So the differences here to the other models that you may have come across in this kind of vein, I mean, Bayesian knowledge tracing is the big EDM model. What they're doing there is they're using Bayes to estimate parameters of a latent trait model. So the model is been developed, and then Bayes is being used to set the parameters, whereas in this case, Bayes is the model. We're using Bayes as the description of our students. Another thing that you may have come across, there's a bunch of econometric and decision theory models that do use Bayes as the model for people, but they're more interested in determining whether people are rational or not rational. So what we do, we give people information and we see if they incorporate it into their schema, and if they do, we can say, yay, people are rationally coherent with Bayes, good for us, we're the best animals in the animal kingdom, something like that. And if they don't, then we need to go back to the drawing board. So now moving on to the kind of, how do we operationalize this idea, which is, this is the tricky bit. The first thing is we need to consider each student as essentially a Markov process. So each student is carrying with them information about all the other answers that they've ever given on a particular topic or a particular knowledge component if you're from that world, or maybe we can just think about it as a belief about the world. Do you believe in climate change? Do you believe in Russian hacking? Something like that. Then what we're going to do is we're going to say, well, we need to count something. So the easiest thing, or the thing that is readily available at the moment, is counting whether students are right or wrong. So that's going to be our sequence that's going to, that we're going to generate a numerical value for, which we're going to call a probability, and that represents the output of this balance between knowledge and context. The context piece is really hard, and what I would, what we would, in an ideal situation, we would only have things to do with one student. In this case, I've used task difficulty, so I've used other students to come up with a number to feed in. Not maybe the best choice, but it's workable. And then what we're going to do is we're going to try and estimate knowledge, the prior knowledge, based on those two values. So how are we going to validate that? There's a bunch of different ways that we could validate whether our prediction is good or bad. There's maximum likelihood. Yeah, that's really not easy to see. Apologies. We use maximum likelihood. We could use other goodness of fit ideas. We're using Bayes already, so that's what I've used here. And I've calculated the conditional probability of the model over-predicting or under-predicting, and then that's what I'm going to feed back into the model to adjust predictions for the next round. So if you're interested in the not particularly optimized code, it's available on GitHub under an algorithm called Snowflake, as in every student is a special snowflake, and we should treat them like that. Yeah, so you can run this, you can use it, you can do whatever you like with it. Here's some simulation results that I've put together from it. The first, the simulations were essentially, we're going to draw random values from a Gaussian distribution where I've set the mean at different levels, and then if it's above 0.5, then this particular modeled student is correct, and if it's below, then it's incorrect. And then what we want to know is, can this algorithm recover those values from just random sequences of data of incorrect and correct. There's some kind of interesting qualitative things straight up that we can look at. So here are 3 simulated students and their knowledge. So one that's at a 0.75, which it seems to have recovered quite well, one at 0.25, which it seems to have recovered quite well. What it does struggle with is the middling belief value. It can't seem to lock on to that. And what digging into that a little bit has figured out is that it's really sensitive to the sequence. So when changes happen, it will kind of take those on board a little bit too quickly maybe and incorporate them going forward. So if you have a middling value, if you have a lot of kind of yes, correct, incorrect, it can't lock on quite as well, but it doesn't shake around. It just kind of goes, oh, it's here. I'm gonna go with that. So looking at what happens if we actually intentionally mess with it, it seems to change quite quickly with a sudden change. So if we say someone's at 0.25, that's their belief, and then they jump really quickly and really high to 0.75, seems to take that on board here, but it struggles with a gradual change. Overall, that didn't seem, when we run this for 1,000 different students answering 30 items, it seems to come out slightly the other way, so it's not quite as good as a sudden increase, and it's slightly better at a linear increase. What I think is happening is that it really just depends, of the millions of possible sequences that you can pull for 30 questions, it's going to be completely dependent on what kinds of sequences you get. There's a finite number of sequences, and which occur in real life more is going to matter for how accurate this model is. So here's some draft stuff on some actual students that have come out of the assessment system at WPI, and one is just to show that the one on the left is just to show that this is what the kind of readout you would get from this algorithm tracing actual students. There's no way to necessarily validate that currently. The other side is to show that if we move away from just having a point estimate to a distribution, we can generate these distributions of belief for students, which could be diagnostically useful in terms of looking to see where students are at and what kind of interventions work. Again, some draft results to show comparison with BKT. And the interesting thing here is that it's basically the same in terms of how good it is overall at predicting students. However, if you're looking at a per student basis, so how good are you at, if I pulled one student and I wanted to just predict that one, it seems to be better than BKT. So possibly the theory behind that would be that we are preferencing the variation across time, which has information about individual students in it, that is lost when we start to use models that go across students as well. So possibly, if you want a general trend, this is not the model for you. But if you want to make a prediction about one particular student in your class, then this is going to be a superior model. But that needs to be gone into more in depth. And below that is showing that there is a slight positive over-prediction skew with this data. So the benefits here are that it'll work even if you have hardly anything. So if the only thing you have is a sequence, then this will work for you. Provided that you can frame it in the terms, so that you can frame it in terms of some kind of student belief or student knowledge that you are trying to predict. Like I just said, it may exceed predictive accuracy for students on an individual basis. And aligned to that is that every student gets their own parameter associated with the model. So every student is getting some kind of estimate as opposed to an estimate that's linked to a larger model that goes across all the students. And possibly because of that, you might be able to make some kind of stronger claim about individual students instead of one that is associated with subgroup or the population at large. I think that. So moving forward, we're going to try and send more student data through it and try different types of topics, different cost functions, distributions, and different likelihood functions, all these things. And then the ultimate goal is to try to figure out if this is a better way of going about trying to personalize your models. So trying to do the bottom-up rather than the top-down approach to modeling. And there's a kind of a side question. It's like, does this actually correspond to anything that students think? Does this correspond to how confident they are or something like that? Right, I think that's it from me.
Great. Thank you, Charles.
Yes.
Thank you for the interesting talk. I know very little about Bayesian analysis, but I was wondering if you could compare it to, say, like dynamic multi-level analysis, where you do model groups of students, you model groups of students, you model moments in time. So, what are the advantages and disadvantages?
I don't know if I can talk to the advantages or disadvantages. So I mean, I think the base level difference here is what I just said. So in the multi-level, that's another strategy for trying to get at smaller differences, smaller subgroups. But you're taking all the variation you have, and then you're trying to carve out the pieces that belong in each level and then to each covariate. Whereas here, we're saying we're just going to start with the minimum level of variation we have, and then maybe we can build up from there. But we're going to try and make a probability statement at the lowest level before we move up to the next level. Does that make sense?
Let's follow that. So with the dynamic multi-level analysis, you can actually do it at the local level. So you can do that each moment in time. And so it's not really lower. Like the Bayesian level analysis is not lower than dynamic multi-level analysis.
Not in terms of time, no. But in okay, I'm unaware that we'll talk, definitely. I'm quite interested. I didn't know that it did that. Okay, thanks. Yes?
Another question, how long do you think this would work in a situation where the student is given more than one attempt at a particular problem? So they might try it once and get it wrong, and then pick another answer and get it right.
Yeah, and that's a really good question, actually. So it depends on how you're going to frame the thing that you're trying to measure. So if you think 2 attempts is a better measure of belief in a particular construct, then fine. But I can imagine that there's times when you are going to have to change it to retest so that students aren't being helped just by the context of having already answered the question. Yeah.
So before you mentioned that students have like a normal process, do you think that that's certainly holds there, or do you not think that the sequence in which they gain their beliefs and their knowledge is actually important? So you need some, if you're modeling it, you actually need to look at something like automation process over a certain number of steps.
Yeah, definitely, but baby steps. Yeah, no, I mean it's a kind of it's a for now assumption. Yeah, Daniel. Yeah, Daniel.
So thanks for that great conversation. Right in this model, you're only including essentially one information, correct? Have you thought about using this model to include more relations on top of something that like, so I had some series of what someone's saying, but also multiple layers mentioned around tried doing that, adding more?
Yeah, so I've tried somewhat unsuccessfully, somewhat on the edge of creating a hierarchical model. So your belief exists within another larger belief. Is that what you're trying to say, or do you mean?
Well, that would be ethical to,
Yeah. So, and the other piece I think is the kind of covariate piece of like what other bits of information is going to be how you characterize the likelihood. So it's going to be what do you think is pertinent to the student, collect data on that and include that. So at the moment it's just difficulty, and that's kind of a gross idea of what the kind of context is for the student. But if you can numerically calculate some kind of probabilistic value that represents the context much more fully, then you can include it there and look to see if that helps or hinders your prediction.
more information at the start of the model. And then you're working on adding more layers of
Yeah, so working on yes. Yes.
Louder, please.
Three questions. One,
Three.
is there any way to feed higher instead of setting them random? And the second question is, how does your model handle local independence or rate violation of independence? Third question is, since you're using items instead of using a time variable, when you use items that have a nested structure, so then a set of items actually share maybe certain units or scenarios, right? So that's another scenario where your model is going
Okay, so first was, I've lost it. Priors, yes, so priors will be easy to incorporate. Have tried it, didn't really make that much difference to anything. It was based on previous tests, so it's kind of an average score. Throw that in, see if you do better. Some students do, some students don't. Second question was? Local independence. Yeah, I mean, that's an interesting question that I don't have a good answer for you. So what would a scenario be? So the scenario would be if we had students who just worked together every day and were in each other's pockets all the time. Yeah, no, I don't have a good answer. Sorry. Is that it?
Oh, over here.
Yes.
I was following your logic up until the point at which you incorporated task difficulty as the context. Just because task difficulty does require knowledge of other students.
Yeah.
What are other contexts potentially thought about, or how else would we think about some parameter of the environment?
Yeah, so this is the real hard, like this is the sticking point that I have now. Because just for logical consistency for me, I want to have a model that only relies on the student. So how do we probabilistically characterize some kind of contextual cue? And it means we have to collect information about the context and then insert that in as part of the sequence. So it's...
Could you use something like the amount of time it takes a student to answer a question, or is that a parameter of the student and not of the context?
No, that's kind of a behavior, but if we could construe it as part of the context somehow, then yes. I mean, it's all part of the student. If we think about it as kind of like the action is the interface between some kind of context and whatever the student's bringing, then yeah, what about the context changes with respect to the amount of time possibly. So maybe if there was a timed web page and it went away or something like that. I don't know.
Just imagining that
estimates and new estimates about the student without prior knowledge about that student, then you're also attempting to collect information based on the student behavior about the environment. So the idea of the amount of time it takes a student to answer a question potentially allows you to estimate task difficulty, in essence, right, based on the idea of how much time it takes. And if that time changes from one question to another, you could make estimates about the difficulty, at least for that student. It's just trying to understand how do you do it really without having...
Yeah, no, that sounds like, at the moment, like a good strategy. So maybe I'm going to write that down. We're going to give it a go. Yeah, if you want to chat after, that'll be great.
Do you want one more? Can we take one more and then
Sure.
let people go? Yeah, go ahead.
You're trapped in here.
I know.
Thank you. So I was wondering, you talked a little bit about Bayesian knowledge tracing, and one of the things with Bayesian knowledge tracing is you require a lot of historical data to train a model, which it seems like it's not really required in your model. So have you thought about how your model could be used to kind of avoid this bootstrapping problem that other models have, where you need students to use the system before you can actually start assessing their knowledge? And also, I guess that could extend in terms of difference in knowledge across different populations of students.
Not sure I understand the second part, but the first part is there is some kind of burn-in, right? Like you need to get some information. At the moment with this data, I think it's probably somewhere to 10 to 15 items before it kind of settles. So that does exist, but maybe fewer because the inference you're making is smaller, but that's a guess.
Okay.
All right.
All right. Well, thank you, everyone, for being here, and let's thank our speakers again, and we have a lot to think about. Thanks. So lunch is in this building. Remember, you don't have to go outside anymore today, or at least in... No, I think at all. Where's the reception? Anyway, for now, it's downstairs where you've gotten food before. We're a little bit early, so maybe it's already up and ready for you.
Great.
Yeah.
I just want to try this. Could the member for Bhutan please take the floor? I'm sorry.
I don't know if those work, but it says